asked us to find the equation of the line tangent to the function x plus square root of x at x equals 4. Now, with any equation of a line, I always need the same two things. I've got to have a point and a slope. And I didn't give us either one in this problem, but I kind of give us half of a point because I give us the x value. So the first thing I'm going to go ahead and do is find that point. So when x is 4, f of 4 would look like 4 plus the square root of 4. So I'm looking at 6. So our point is 4 comma 6. And if I think about just generally what the equation of that line is going to look like, I'm going to have y minus 6 is equal to the slope times x minus 4. Now comes the calculus part. In order to find the slope of a tangent line, that means I'm looking to take the derivative and evaluate it at x equals 4. So now for the derivative part. The first thing that I'm going to choose to do is to rewrite this, because anytime I can make something look like a number times x raised to a number, I know that I'm going to be able to use the power rule. So looking at this, I could rewrite that as x plus x to the 1/2 power. And now I'm ready to take my derivative. And I'm looking at 1, because the derivative of x is just 1, plus, I'll bring down that exponent, the 1/2, x, subtracting 1 from 1/2, I get negative 1/2. I find that the square root of x as a function shows up often enough when we're taking derivatives that I kind of actually add it to my list of derivatives to memorize. And so for me, I think of this really as the derivative of square root of x is 1 over 2 root x. It is totally fine to just do it with the power rule each time. This is just one that shows up enough that I like to have it in my arsenal of like quick facts for derivatives. So in terms of getting that slope, I need to take f prime and plug in 4 for x. So I'm looking at 1 plus, and if I leave it in this notation, that's fine, 1/2 of 4 to the negative 1/2. But in order to evaluate that, I probably actually want to be thinking about it as 1 over 2 square root x. Because 4 to the negative 1/2 says, okay, the negative says put it at the bottom of the fraction, and the 1/2 power says take the square root. So if I take the square root of 4, I get 2, and then the negative, meaning put it on the bottom of the fraction, I'll have 1 plus 1/2 times another 1/2. That's 1/4. 1 plus 1/4 is going to put me at 5/4. And that's what I'm going to plug in for my slope. So I would write the equation of the tangent line as y minus 6 equals 5/4 of x minus 4. And that would be my final answer. Didn't use the product rule, then really our only option would be to multiply all of that out and then take the derivative. So I'm going to do it that way first. So if I were to multiply all of that out so that I could simplify it before taking the derivative, 3x times x squared, that's 3x cubed, and then minus 3x plus 5x squared minus 5, and then I could take a derivative. And if I did that, 3x squared, my 2 is going to come down, multiply by the 3, subtract 1 from the exponent. So I'm looking at 6x minus 3. 2 times 5 will give me a 10, x to the 1, and the derivative of a constant is 0. So I get that right? I did not get that right. I caught my own problem. You all are supposed to catch me when I make mistakes. 3x times x squared is in fact 3x cubed. So let's go back in time. Multiply that out correctly. 3x times x squared is 3x cubed, which means when I take that derivative, 3 times 3 will give me a 9 down in front. And then subtracting 1 from the exponent, I'll have an x squared. If we were to instead use the product rule on this, our function, we've got 3x plus 5 times x squared minus 1. If you've done a bunch of product rule in a previous life, definitely you do not have to take it as slowly as I'm about to take it. If this is the first time you're doing derivatives or the first time you're seeing product rule, one of the things that I think helps is to just go ahead and get all of the pieces kind of where they're going to go. So when I take that derivative, if I've got a product rule, I know I'm going to have 2 things plus 2 more things. And then in terms of the formula, I know I need f prime g and f g prime. So I'm going to put in the 2 pieces that don't require a derivative yet. So if that's f and that's g, I'm just going to go ahead and write my f in 3x plus 5, and I'm going to go ahead and write my g in x squared minus 1. Now I'm ready for the derivatives. So the derivative of f, just f, derivative of 3x plus 5, it's a linear function. I know how to find the slope. It's that coefficient on x. Over here, I've got x squared minus 1, not a linear function. I'm going to use my power rule. And the derivative of x squared would bring the 2 down in front, subtract 1 from the exponent, and I'm just left with 2x. Now you might be staring at that and saying, they don't look the same. But if I now take a minute to multiply this out, I would have 3x squared minus 3 plus 6x squared plus 10x. And now if I put my 2 x squared parts together, these 2 are going to match. Now, if you just have polynomials and it's something that isn't so bad to multiply out, it doesn't really matter. Would you rather do the algebra up front or would you rather dive into product rule? But if our functions are anything more complicated than polynomials, we're going to end up having to use the product rule quite a bit. Okay. So let's go ahead and plug our pieces in. So I'm looking for f prime here, and I take that derivative just using power rule. So I'll multiply my 2 down, 2 times 3, I'll get 6x to the 1 power. And just for completeness, I'm going to go ahead and write this as plus 0 because the derivative of a constant is 0. G of x is sine of x. And now I'll write f, 3x squared plus 1, and my g prime. So the derivative of sine of x is cosine of x, and we talked about that just a little bit last time. In general, there's no reason to do any algebra beyond that. If the entire question is just asking you to take the derivative, we get to be done. Not too crazy. So when I take that derivative, I'm personally going to go ahead and just give myself the space. Oops, missed a plus sign, didn't leave myself quite enough space there. And I know that these pieces have to look like f prime g plus f g prime. Now notice I'm saying f and g, but my function is called f of x. We're just going to have to live with it. Most of the time our functions are called f of x. We're just going to think about that derivative, whatever the first piece is, that's what I'm calling f for the formula. Whatever the second piece is, that's what I'm calling g. So the derivative of e to the x is e to the x. Again, we're going to memorize that. Then we'll leave the x cubed alone. Then I'm going to leave the e to the x alone and take the derivative of x cubed, which is 3x squared. Good times. Since we did the formal derivation for the product rule, I'm not also going to do that with the quotient rule. I will tell you that it works out the same way, that we're going to add 0 creatively, regroup the two parts to end up with the derivative of something that looks like f divided by g. Looks like, again, I've got 2 letters, so I'm going to write them twice. What usually goes with division is subtraction. I'm going to chase down the derivative and put the whole thing over g squared. If that looks like magic, it is magic. I promise it comes from the limit definition of the derivative. We don't need to go through all that algebra right now. You're going to need to memorize this. Now, there are fun little sayings and songs to help people remember the quotient rule. Here's my advice. For the product rule, because we're adding things, it doesn't matter what order we put them in. But for the quotient rule, it matters because we're subtracting. So for me, I just like to keep both of them in the same order so that I kind of only have one order to memorize. Totally up to you. So let's get some practice with the quotient rule. And let's say that my function is e to the x minus x squared all over x to the 4th plus x. So I've got division going on. So I know right away I'm thinking about a quotient rule. And again, if you're just getting started practicing with derivatives, I recommend just giving yourself the space. Sort of give the format of what we know the answer is going to look like. So I'm going to call the top my f. I'm going to call the bottom my g. And this needs to look like f prime g minus f g prime all over g squared. I'm going to put in the stuff that doesn't require derivatives. So x to the 4th plus x will stay on the bottom. It'll go up here. And my e to the x minus x squared will go there. And then I just need to sprinkle on the calculus. So the derivative of the top, the derivative of e to the x is e to the x. And the derivative of x squared is 2x. Derivative of the bottom, I've got x to the 4th. So I bring that 4 down in front and subtract 1 from the exponent. And then the derivative of x is 1. And then we walk away. Unless there's something about the problem that tells us we need to be doing more algebra than that, we're going to quit at that step. There isn't really any point in distributing things out. A lot of times it's not going to simplify anyway. Now that we've got the quotient rule, it also means that we can get all of the rest of our trig derivatives. So that's where I'm going to go next so that we can add to our list of stuff to memorize. So let's say that my function is tangent of x. By the way, I've seen this show up as a quiz question before to use the quotient rule to derive the derivative of tangent of x. So we need to start by the trig identity, knowing that tangent of x is the same as sine of x divided by cosine of x. And then I'm going to use the quotient rule. So I know on top, I'm going to have some stuff minus some stuff. And then on the bottom, I'm going to have some stuff squared. We can do the simplification together, but go ahead and put all the pieces in where they go on your paper. Okay, so in our quotient rule, I'm going to start by taking the derivative of the top. And again, we're going to want to memorize these trig derivatives. So the derivative of sine is cosine. And I should complete that statement. I'm leaving something really important off. The derivative of sine of x is cosine of x. Then I leave the bottom alone, minus, leave the top alone, times the derivative of the bottom. And the derivative of cosine of x is negative sine of x. In the denominator, I'm going to end up squaring cosine of x. Now, this is not usually how we memorize the derivative of tangent. We're going to use some trig identities to clean this up a bit. So on the top, notation-wise, if I have cosine of x times cosine of x, we often write that as cosine squared x. I've got a minus and another minus, which will turn that into a plus. And sine of x times sine of x, we can write as sine squared x. And then on the bottom, I'm going to leave that as cosine of x squared just for a minute. The top should jump out to you as a trig identity. What is cosine squared plus sine squared? It's a number. Totally. So cosine squared x plus sine squared x is 1. And it's really, if you only have one trig identity memorized, that's the one we want. So sometimes it's called the fundamental trig identity, but it's definitely the one that shows up a lot. Now this next step, it would be totally fine for you to memorize the derivative of tangent like that, but nobody does. Because 1 over cosine is equivalent to secant. And so we really think about this as secant squared x. So now we are, and we can derive the derivatives for cosecant and secant and cotangent all using the quotient rule. And maybe that's worth your time sometime, but really the expedient thing is we have to memorize these derivatives. So I'm going to write them all down here. Again, back to, we're going to memorize these. So the derivative of sine of x is cosine of x. The derivative of tangent of x, we just did, that's secant of x. The derivative of secant of x is secant x tangent x. And then we have all of the cos. So our, those in a different color. So the derivative of cosine of x is negative sine of x. The derivative of cotangent of x is negative. Oh, I mixed a squared. Again, you all are supposed to catch my mistakes for me. We just found that the derivative was secant squared x for tangent of x. So the derivative of cotangent of x is negative cosecant squared x, and the derivative of cosecant of x is negative cosecant x cotangent x. Now I've written them intentionally kind of in these pairings because all of our co-functions, the derivatives are negative. And I kind of think of that negative as a light switch that is flipping from the function to the co. So my secant squared, when I've got the cotangent, I flip the light switch. So my secant squared, so my secants change into cosecants. When I'm looking for the derivative of cosecant of x, it's a co, so I flip that light switch. My secant turns into a cosecant, my tangent turns into a cotangent.